All right, so we're in section 11.5 now. We're looking at the at alternating series and absolute convergence. In this section, we're going to be developing another tool to test series for convergence, but it's for a specific type of series. So let's start with a definition. We have these things called alternating series, which are series in which each term will alternate between being positive and negative. So if you notice this series right here, we start with a positive 1, then a negative 1/2, then a positive 1/3, and then a negative 1/4, and so on. They don't have to start with the positive term. They can start with the negative term, but they just need to alternate each term for term between positive and negative values. When we write these in summation notation, we tend to see something like this, -1 to a power involving the n somehow. So it could be -1 to the power of n, or -1 to the power of n minus 1, or n plus 1, things like that. Because if you look at either of these, let's take -1 to the n, for example. Every time the exponent n goes up by 1, we're going to be changing that exponent between odd and even numbers. So for example, when n is equal to 1, we're taking that -1 and raising it to the power of 1. Since 1 is an odd number, -1 will stay -1. But every even power that we plug in for n will make this -1 into a positive 1. And this is how we get that alternating between positive and negative values. The reason we may want to use an n minus 1 or an n plus 1 instead of an n is if we want our series to start at a positive number instead of a negative number. Notice here, if I plug 1 in for my exponent, I get 1 minus 1, which is 0, and -1 to the power of 0 is positive 1. That gives me a positive first term. So you'll see this notation, or this type of thing showing up in your summation notation a lot in this section. So alternating series, it turns out, are generally a little bit easier to determine whether they converge or diverge than some of the other series that we've looked at. And here's the reason why. We have this thing called the alternating series test. So suppose you have an alternating series, and this is the one that we're being shown here, but that -1 to the n minus 1 can be replaced with a -1 to the n, or anything else that gives me an alternating series of terms, even if the first term is positive or negative. So this can be generalized a little bit further. So the series would look like this: B1 minus B2 plus B3 minus B4. You see the alternating pluses and minuses there. And then the BNs we assume are all positive here, because the negatives are being accounted for by putting minus signs where we need them to be. If this series satisfies these two conditions, so 1, bn plus 1 needs to be less than or equal to bn for all n. So what that means is if we take the absolute value of all of our terms, or if we just think of all of these bn's as positive, like we're saying right here, then the sequence of terms should be decreasing. So these terms should be getting smaller and smaller and smaller. And then in addition to that, if the limit as n goes to infinity of that sequence of terms goes to 0, then that series is automatically convergent. Now, we've seen this condition before, but it was actually in our test for divergence. We said a ways back that if you have a series and you know that the series is convergent, then the limit of its terms, or the limit of its sequence of terms, has to go to 0. And then we said that the converse of that is not necessarily true. In other words, there are series, the harmonic series is one example, where if you take the limit of its sequence of terms, the sequence of terms will go to 0, but the sum may still diverge. So we said that just testing the limit, the sequence of terms, if you see a limit of those sequence of terms going to 0, that doesn't necessarily mean anything. But here it actually does. If you have this condition in addition to this one, that's how we know that an alternating series will converge. Here's a proof of this down here. So as we've been doing, anytime we want to prove one of these convergence or divergence tests, we look at the partial sums of our series. So let's start by looking at just the even partial sums, like S2, S4, S6, those sorts of things. The reason I'm doing that is because when I have an even partial sum, I can group up the terms of that partial sum in pairs, and I can specifically group up consecutive pairs that have a minus between them. So for example, S2 is the sum of the first two terms in my series, which would look like B1 minus B2. Okay, now remember, from our first condition, we're assuming that both of these conditions are in place. This first condition here, every new term in my sequence of terms has to be less than or equal to the term that came before it. So that would imply that if I subtract them in this order, B1 minus B2, I should get a non-negative value. B2 is less than or equal to B1. So this S2 here is going to be non-negative. If I look at S4, it's equal to B1 minus B2, which is the same thing as S2, plus B3 minus B4. And using the same reasoning here, this term, this B3 minus B4, has to be greater than or equal to 0, which means S2 plus that would be greater than or equal to S2. And I can continue on in this fashion, going to each new even partial sum. And what I'm going to see is that each even partial sum is going to be greater than or equal to the one that came before it. So S6 will be greater than or equal to S4, and S8 will be greater than or equal to S6, and so on. And written generally, S2n, so where n is any integer, 2n would be even then, is going to be greater than or equal to Sn2n minus 2. This would be the even number that comes before 2n. Okay, so if I look at just the even partial sums, then I get this relationship. They're all positive, or non-negative is a better way of saying that, and then they're kind of an increasing sequence of partial sums if I'm only looking at the even ones. Okay. Alternatively, I can also write any even partial sum this way. So remember, up here I was grouping terms up in a specific way. Here I'm going to group them in a slightly different way. I'm going to leave the first term alone, then I'm going to group up the next two terms. If I come up here and look at what that would look like, negative B2 plus B3. If I were to group up those two terms and factor a negative out, I'm going to get this, B1 minus B2 minus B3 in parentheses. Notice that negative would distribute back in to give me a positive here. And then I do that for all of these other pairs of terms. Now, because this is an even partial sum, there should be an even number of terms. I've left one of them out. So if I include that one and then all of these pairs, I would have an odd number of terms. To get that even number that I'm expecting, I'm going to have that last term out here, minus B2n. Okay? As before, all of these grouped up terms are going to be non-negative, and that's again because of this first condition right here, that's going to be the case. So what does that mean? Well, I have B1 minus a whole bunch of non-negative terms, which means if I'm only subtracting non-negative values from B1, then this whole thing has to be less than or equal to B1. There's no chance of it being greater than that if I'm subtracting non-negative numbers from it. So here's what that tells me. The sequence of these even partial sums is increasing because of this relationship that we talked about here, but also bounded above because the even partial sums will all be less than or equal to just that first term of our series, B1. So we can apply the monotonic sequence theorem here and say that those two conditions imply that this sequence of even partial sums has to converge to some limit, which we're going to call S. And here that is stated using the limit notation. Okay. Now we're going to repeat this process, but we're going to look at the odd partial sums because we've left those out so far. Now the odd partial sums, you can think of any one of those as an even partial sum plus the following term. So Sn2n plus 1 is just equal to the 2nth partial sum plus the next term in the series, b2n plus 1. The limit of these odd partial sums is the same as the limit of this sum here. I can distribute the limit over sums. We know that from Calculus 1. We just said that this limit here as n goes to infinity of this even partial sum is equal to s. And in addition, the limit as n goes to infinity of b to the b2n plus 1 is 0. And that comes from this second condition here. because if I take the limit as n goes to infinity here, then that's the same thing as the limit of the sequence of terms for this series. S plus 0 is, of course, s. So the limit of each of these two sequences agree. Since both the even and the odd partial sums converge to s, then the limit of the sequence of partial sums itself, not just the even or the odds, must also be s. So that would imply that this series is convergent. That proves the alternating series test, but there's a good way of visualizing it as well. So let's suppose that we're looking at our partial sums of our alternating series on a number line. So the first term is b1. If I think of that as 0 plus b1, that's going to take me over here to my first partial sum. And then I know that the next thing that's going to happen, because I'm talking about an alternating series, is I'm going to subtract a non-negative number. So I'm subtracting b2. Now that b2, one of the conditions of our alternating series test said that b2 has to be smaller than b1. So by subtracting it, I'm moving to the left on this number line, but not far enough to get back to b1 again, because it's going to be a smaller distance. Then after that, I add a positive term, b3. Positive means it's going to move me in this direction, but b3 is less than b2, so it's not going to get me as far as where we started when we subtracted that b2. It's going to take me maybe to here. That's my third partial sum. And then you continue on in this fashion. You're going to see that it's sort of ping-ponging back and forth, but going a shorter distance each time. And what's going to happen is that because these terms, the sequence of those terms goes to 0, these distances are shrinking to 0 somewhere to this limit s. And if you notice, that value s is between, it's kind of trapped in between these partial sums over here. If you see all the even partial sums, they're appearing to the left of s, and all of these odd partial sums are appearing to the right. So that s is going to be trapped somewhere in between them as these zero in on that limit. Okay? So let's start with an example. We're going to do a few examples. Determine whether the alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4 and so on, converges or diverges. The alternating harmonic series is just the harmonic series where we alternate between positive and negative values. We know that the harmonic series diverges, but does the alternating harmonic series converge or diverge? So for this, we need two things. We need to verify, one, are these terms decreasing? If I'm ignoring the positive and negative, so if I think if this is 1, 1/2, 1/3, 1/4, and so on, are these decreasing? Well, 1 is greater than or equal to 1/2, which is greater than or equal to 1/3, which is greater than or equal to 1/4, which is greater than or equal to 1/5, and so on and so forth. These definitely have the trend that we're looking for. They are decreasing when I take all of their absolute values. So that works. And then 2, what is the limit of, as n goes to infinity, of this sequence of partial sums here, or a sequence of terms? So how do I represent these terms kind of generally? Well, we know that because it's an alternating series, it's going to start with -1 to some power, either an n or an n plus 1 or an n minus 1. I want my first term to come out positive, so it's not going to work to just put an n there, because if my sum is going to go from n equals 1 to infinity, then my first term would end up being negative. I'm going to add a 1 to that to make sure that I start with a positive term. And then the remaining terms just look like 1 over n, right? So what is the limit of this sequence? Well, the only place that n shows up is here and here. The n's here are only causing this to alternate between positive and negative, so that's the only thing that's happening there. But here, as n gets larger, this is going to be approaching 0. Whether you're getting a positive or a negative in front of that, it's still approaching 0. So that is the second condition of our alternating series test. I can say, by the alternating series test, the alternating harmonic series converges. Yeah. Okay. Okay, let's try another one. We're going to test this series for convergence. So this is an alternating series. because we have that -1 n to the power of n plus 1 there. And then I have arctangent of n as the rest of that little formula. So this one, well, one thing I want to point out is that if a series diverges, even if it's an alternating series, the alternating series test may not necessarily show us that. Instead, we want to use like the test for divergence, and that's actually what's happening in this case. If I were to look at the limit at the sequence of partial sums here as n goes to infinity of -1 to the n plus 1 arctangent of n. Remember, of one of our conditions for the alternating series test would say that this has to go to 0. But does this go to 0? Well, it doesn't. So the reason I know that, what if n is an odd number? If n is odd, then this is going to be odd plus odd, which is even. I'm going to get a +1 arctangent of n. So this is equal to the limit as n goes to infinity of just the arctangent of n if n is even. And if n is odd. What about if n is even? What can we say in that case? Well, if n is even, then this is going to be an odd power up here, so I'm going to get a negative arctan of n if n is even. Okay, but what is this equal to? Well, the arctangent function is a bounded function. It has a finite limit as n approaches infinity, or negative infinity, but in this case we have n approaching infinity in both cases. And if you remember, the limit as n approaches infinity of the arctangent function is pi/2. Again, this is if n is odd. In this case, I have a negative out front here, so for that other case, n is going to approach, or arctangent of n is going to approach -pi/2. But in neither case are we getting 0. So this would tell me that this series diverges. And this one's by the divergence test. Okay, because the divergence test says that if a series converges, then the limit of its sequence of terms has to go to 0. So if we don't see that happening, then the series must be divergent. Let's try one more. This series right here, I want to test for convergence. It's an alternating series because I have -1 to the power of n there. So this one, let's see. Let's start by comparing these terms. Is the square root of n over 2n plus 3 greater than or equal to the square root of n plus 1 over 2 times n plus 1 plus 3. So if this is the nth term, then this is what the n plus 1th term would look like, because I'm replacing these n's with n plus 1 to get that. Is this true? How do we determine that? Well, there's a couple of ways of going about it, but one approach is to use calculus. And what I mean by that is if I replace the n's with x's, so f of x equals the square root of x over 2x plus 3. If I take the derivative of this, and if the derivative is negative, everywhere where I need it to be negative, so that would be if x goes from 1 to infinity, that would imply that this function is decreasing on that interval, which would also mean that these terms are decreasing as we proceed through that sequence of terms. So let's see what happens. If I take the derivative, f prime of x, I can use the quotient rule here. So low d high, this is 1 over 2 root 2, minus high d low. Whoops, sorry, I made a mistake here. This should be 2x plus 3 there. And then d low, that would be 2, all over low squared, 2x plus 3 squared. Can I simplify this a little bit? Let's see. I'm going to get 2x plus 3. This should be 2 root x right there, over 2 root x minus, now this is 2 root x, but if I wanted to get a common denominator, I would multiply it by another 2 root x, like this. Okay, so now I can multiply this. This would give me 4x here. And then I can subtract some stuff. So let's take this 2 root x, bring it down here. And then when I subtract this minus this, I'm going to get negative 2x plus 3 over 2 root x times 2x plus 3 squared. Now, is this a decreasing function on the interval from 1 to infinity? So notice if I plug a 1 in, I'm going to get, well, actually, let's do this a little bit differently. When is this thing negative? Notice that my denominator is only ever positive, right? I want to know when it's negative. This is only ever positive. So this expression will be negative only when my numerator is negative. But that means I can take this negative 2x plus 3 and set it so it's less than 0 and then solve for x. If I do that, I'm going to get x is, what would that be? It's going to be less or greater than 3/2. Okay, so it doesn't start decreasing until after the first term because 3/2 is greater than 1, but then it starts to decrease. And even though the convergence, the alternating series test says that we need these terms to be a decreasing sequence, if the first finitely many terms don't follow this trend, but then eventually those terms do, this alternating series test still applies. So as long as we're eventually decreasing, then we are in good shape here. So that would imply this. As long as n is greater than 1, this is always going to be true. What about the sequence of terms themselves? What can I say about the limit as n goes to infinity of the square root of n over 2n plus 3? This is an indeterminate form. It's an infinity over infinity type, so I could use L'Hopital's rule, or alternatively, I could multiply by something that simplifies this, like maybe 1 over root n over 1 over root n. This would be equal to the limit as n goes to infinity. These are going to cancel and just give me a 1 there. 2n over root n would be the same thing as 2 root n after simplifying, plus 3 over root n. Now as n goes to infinity, the denominator of this term right here is going to get really, really large, and my numerator is going to stay at 3. So this will go to 0, which means this is basically going to look like 1 over 2 times root n when n is large enough. But then as this value gets really, really large, the denominator gets really big, and so the whole thing is going to go to 0. The limit in this case is equal to 0. So we have both conditions in place. I can say that this series converges by the alternating series test. Okay? All right, so there's a few examples under our belts. Let's end this video here. We'll pick up where we left off in the next one.